you see and describe it to me in one phrase.
This is a yellow bottle with water filled in it.
Did you say, this is a yellow bottle with water filled in it?
Yes. Yes.
I am turning to face table 1. Would you use the word bottle to describe this object?
Yes.
Testing, testing. Sound good? Thanks. Okay.
And just want to make sure that's on the pocket opposite from your cell phone.
Yeah.
Okay. Just because sometimes that causes
Interferes, yeah.
Just
Okay,
we
I'm
actually
good.
Move it up just a little bit.
Sure.
Yeah.
Sound good? You know Peter?
I know my son's a PhD student.
Oh, okay. Hi, Ray. Yeah, Mike's a great guy.
We'll probably wait for a few more.
Sure. I was at Caltech on Monday, and I was at UCLA on Tuesday. No. I got to get back to teach classes next week. I'm teaching a seminar on grounded language. It's relevant to this stuff, yeah. This is still working, right? Whenever you're ready. My seat's up here.
All right, so let's just get it started. So welcome to the inaugural distinguished lecture by the Center for Responsible Machine Learning. Today we're extremely honored to have Professor Ray Mooney from UT Austin to join us. So I'll just say, briefly introduce Professor Ray Mooney. So he has a extremely distinguished career in the field of machine learning, natural language processing, and also he's very active in the area of language and vision, which he will be talking today. So he did his undergraduate, master's, and PhD degrees at University of Illinois, Urbana-Champaign. And also he is a past president of the International Machine Learning Society, now is the board of ICML, and he is a fellow of the AAAI, ACL, and also ACM. He's extremely prolific, published many papers, hundreds of papers, and also including some of the classic paper awards and best paper awards at major AI and machine learning conferences. So today, he's gonna share with us on the topic of robots that learn grounded language through interactive dialogue. And what I want to emphasize is that I think this really fits perfect with the mission for the Center for Responsible Machine Learning, because a lot of this interesting application can be very beneficial for people who with, visually impaired disease, or maybe, for example, in disaster relief situations, if a robot can really understand language, understand the visual environments, that can really do a lot for us. So without further ado, let's welcome Professor Ray Mooney.
So thanks, William, for the not very nice introduction. I'm happy to be here. This is my first time on the UCSB campus. So I want to talk today a little bit about our work on robots that learn grounded language through interactive dialogue. And when you work with robots, you need a big team of people to do all this stuff. So I won't list all the names there, but Jesse Thomason is the lead on this project. He's now a postdoc at UW. He's on the job market this year. Aishwarya is a PhD student of mine who's finishing up this year. And then I'll particularly mention Peter Stone, my faculty colleague at UT, and then a number of other grad students and postdocs were also involved in this project. So the idea is to try to get a robot to understand commands in natural language, specifically we've just worked with English, without having to annotate a bunch of data. So most NLP systems, including robotics ones, require large amounts of sort of pre-assembled, manually labeled training data. And that's laborious, and it also may not capture the knowledge that's needed during actual end use. You put it out in the field, and then you realize that it didn't quite have the right training data that it needs to do the problems that it has, and then you're sort of stuck except going back and annotating a bunch of new data. So ideally, we want to have a robot that's been trained on relatively little data. It's not really that good at understanding language commands, but we just throw it out into the world and let it interact with people, interact with users. And if it doesn't understand what they're asking, then it engages them in a dialogue and asks them questions and then clarifies things. And then eventually over time, just by interacting with its normal set of users, it gets better and better and better by learning from that interactive dialogue that it's having with its user community. So that's sort of the larger spirit that's behind this work. So particularly with my colleague Peter Stone, he built this robot over here. It's based on a Segway. It has a Canova arm on it, and it can wander around our office building and navigate to various rooms and pick objects up and take them from one place to another. So a lot of these tasks are sort of navigating tasks and moving objects from place to place are sort of the tasks that we've sort of looked at as sort of a set of tasks to look at in terms of commanding. And so we want a naive user to be able to tell this robot to do something. So here's an example of a natural language command. Go to Alice's office and get the light mug for the chair. And this was particularly constructed to make certain ideas. There's a lot of ambiguity in natural language, right? Light mug. What are two possible meanings of that? Lightweight or light colored, right? Chair. Do we want to deliver this to one of these things? The idea is this means the chair of the department. I think we have the chair of your department here, right? So, words in language are ambiguous. You have to interpret them in context. So how do we get a robot to understand these sort of ambiguous, complicated natural language commands without having to pre-train it on tons and tons of labeled data in advance? So that's sort of the goal. So there are lots of issues. Commands need to know how to connect words to actions, right? There's verbs here like go and get. It needs to know how to interpret those so that the robot can actually execute those actions. It needs some world knowledge. It needs to know, we do assume that it has like a database of the information about our building, which is the office names for each of the people. But it has to look up someone whose name is Alice and then look that up in the database of offices and find out what office Alice is in so it knows where to go. And then the chair, it needs to know who the chair, and first it needs to realize that that's talking about the chair of the department. And then it needs to realize, I have to look up where is the office number for the chair of the department, and then it needs to know to take that cup there. And it needs to figure out how does it connect words to perceptual information. Like William said, I've done a lot of work in grounding and vision. How do we interpret what light mug is? And also, does it mean lightweight or light color? So you have this grounding problem of how do we connect words to perceptual information and know how to identify with the light mug in the world based on that linguistic description light mug. And those are all hard problems. So we've been working in this area of commanding robots in natural language, and it's sort of at the intersection of a number of areas of sort of course NLP, then robotics and vision, and then there's also a lot of work which is, you can argue, maybe part of NLP, but there's a whole community that looks at dialogue, right? And so our work is sort of in the middle of all of that, trying to do language processing with dialogue connected to robotics and vision. And we've published a number of different papers associated with different aspects of different parts of this intersection, and I'm just going to talk about a few of them today here. So first, we're going to talk about this sort of mainly this intersection between this NLP, robotics, vision, and dialogue, where we look at improving semantic parsing through dialogue and then improving grounding with human interaction. So I'll go over two papers. One was at IJCAI a few years ago, and one was at, I don't know if people have ever heard of Coral. It's a relatively new conference on robot learning. It's grown quite rapidly just in the last few years. So let's first talk about this improving semantic parsing through dialogue. So if we build a dialogue system for robots, the user come in, they type in some natural language. We need some basic language understanding to extract some sort of meaning from that. So I've done a lot of work over the past 20 years on what's called semantic parsing, which is mapping English natural language to some sort of formal command language or formal representation in logic or program language or something that is a more formal representation of its meaning. Then that goes to some dialogue agent that then understands that and sort of it changes its belief about what that user wants. but maybe it doesn't fully understand what the user wants. So it may then some dialogue policy has to decide, do I understand what this person wants well enough to actually go out in the world and do it? Or do I need to engage them in some clarification about it? So it has to decide whether it's going to ask the user a question or whether it's going to, okay, I understood what you want, I'm going to go off and do it. And then once it decides that, it can go off, send that to the behavior, and then have the robot actually execute the task once it's decided it's actually understood what the user wants. So here's an example. Walk to the kitchen by the lab. It flaps it to some formal command language that the robot understands. I'm not going into all the details. This is a simplification of the actual language, of the formal language. But it's like, I need to do a navigation task. And I need to go to this particular room 3 because it's resolved that the kitchen by the lab is this particular location in the building. And then it says, oh, it basically updates its belief to say, I think this is what I want to do. I need to navigate to there. So, maybe it's not completely sure about what the kitchen by the lab means. So it asks the user, you want me to go to room 3? So then maybe they say yes. And then they go, OK, I understand what you want. And it goes off and does that. OK, so first we need to talk a little about this natural language understanding box. So that needs to take a sentence like this natural language sentence, walk to the kitchen by the lab, and produce some formal representation of that the robot can understand. And then sometimes that needs to be connected to world knowledge in order to get the formal definition. So first we do semantic parsing, and that maps it to something like, here's just the English characterization of the formal specification, which is something, I need to navigate to something that is both a kitchen and adjacent to the lab. Then it needs to know this knowledge base about the building to find something that is labeled as a kitchen that is also adjacent to something that's labeled as a lab. And then it through some, basically deductive techniques on that knowledge base, it says, OK, I know that's room 3. And then it actually has a formal command that it can have the robot execute. But semantic parsing, there's been a lot of work. It takes a lot of annotated data to get these things to work, to map from ambiguous, paraphrasable natural language into one formal command. So we want to try to minimize the amount of annotated data. So we just do, sort of an experiment, we just annotate 5 sentences. This robot can only do a few tasks. It can go to rooms. It can deliver objects from one room to another. It can bring an object to a room, to a person. There's just a few types of commands it knows how to do. But we're going to give it very little supervised data to train on. But of course, it would need more training data. But we're just going to throw it out into the world to interact with people to try to collect more data that it needs automatically through actual use. And then we know the data is actually grounded in the actual utility of what this robot's trying to do. So we design a dialogue policy that allows us to automatically induce new training pairs of human language with latent meaning representations from its interaction with users in the normal day-to-day use. And then improve the semantic parsing given very little initial training data. So doing this with the real robot is a little bit complicated. It's a lot of logistics. So sometimes we run experiments in simulation and then on a larger scale, and then we do smaller scale experiments on a lab just to make sure it works with the real robot. So the main thing that we showed that how this can learn from dialogue, because ideally we'd have a whole army of robots out there in the world talking to lots of people, and then we'd have lots of dialogue with lots of users, and we'd collect all this data. But we don't really have the hardware infrastructure to do that now, so we do this in simulation on Mechanical Turk. We put up a task on Mechanical Turk where we show them a little array of a set of objects. And we don't want to tell them how to refer to these objects, so we give them pictures. And then we tell them, a specific task that we want some particular person to be delivered some item in this array. So particular, we tell them Dave Daniel wants the item in slot 5. And so this is a sample dialogue we had with an actual Mechanical Turk person on Turk, trying to get the robot to understand that this is the task that they want. So the robot says, how can I help? And they say, please bring the item in slot 5 to Dave Daniel. Clearly, this user did not understand what we wanted them to do. We wanted them to describe the object in slot 5 for the robot, not say, item in slot 5. Oh, but that's interesting. Can the robot recover from that misinterpretation? OK, it engages them in a dialogue. It's like, OK, I know you want me to deliver something. So the robot comes back and says, what should I bring to Dave Daniels? And they say, calendar. You notice something wrong with that, though? It's misspelled. Uh-oh. Now, maybe if we had a good spell corrector, this would work. But let's see if just the normal dialogue policy can work with this. So it says, robot says, I'm sorry, I couldn't pinpoint what you meant. What should I bring to Dave Daniel? They say, a day planner. It doesn't know that. I'm sorry, I couldn't pinpoint what do you mean? Oh, they finally realized, oh, they misspelled it. They said calendar. So it basically has just 1 or 2 words to referring to these objects, and it's going to learn paraphrases from just interacting with users naturally. And then it realized, oh, you want me to bring the calendar to Dave Daniel? Say, yes, I thought so. And then, okay, now I understand what you want. It sort of pretends that it goes off and does that. See, but it engages the user in this dialogue. When it doesn't understand, it asks questions. And now what we want to do is learn from that. So we want to learn that when I originally asked, please bring that item in slot 5, what they really meant was bring the calendar to Dave Daniel. So now it has training data that it can learn from, so the next time it does better. And it's also, oh, maybe calendar misspelled actually means the same thing as calendar. So I can actually learn a lot that will help me in the future, hopefully, be more robust by learning from this dialogue. Oh, now it realized that day planner must mean the same thing as calendar, too. So actually, from this one dialogue, it can actually learn some additional training examples. So now what we do is we add new training data, and we retrain the semantic parser, saying, OK, bring slot M means this, calendar means that, day planner means that. Now we add all that data. We retrain. Hopefully, now it's getting better. And we have lots of dialogue with lots of people. Hopefully, slowly over time, it gets better and better and better. So here's a little experiment we ran to sort of verify how well this technique works. We had conversations with 50 people. And then we retrained, and then we did it again. So overall, we had 4 times 50, or 200 total conversations. And we just did batches of 50 just so we could test after each batch. We could do it after every conversation, but that would just be onerous. So we just said we sort of did 4 points on a learning curve, basically, after 50 conversations, after 100, after 150, and after 200. Okay? And then every time, hopefully at every trial, it's getting better and better because it's just talking to people, learning more about this domain, how language people use to refer to things, and getting better over time. So this is sort of showing the learning curve on, we asked the Turker at the end of every conversation, do you think the robot understood them? And they can go do a Likert scale from strongly disagree to strongly agree. And then we see over the batches, as it's training and training and training, it's getting a little bit better. People feel like the robot's understanding them a little bit better. This is for delivery tasks, which are a little bit harder, where you're delivering some item from one place to some person. This is how long the conversation is. So when it starts out, it doesn't know very much, so it has to engage in a bunch of this back and forth clarification, right? So in the first batch, it takes 18 turns to eventually understand what somebody meant. But then in the second batch, it only takes 5 turns. The third, 5.2, then we're down to 3.8 by the third batch of 50 training conversations. So just by talking to people over time, it's getting to understand them better and better. And that conversation gets shorter and shorter, and it gets to the goal of understanding them much quicker. Okay? So that was experiment and simulation. We also ran a smaller scale experiment with the real robot. So we had 10 users interact with the baseline system with no additional training to sort of put the ground of what baseline is. Then we had the robot roam around the office for 4 days. It had 34 conversations with users in the office that ended in training goals. And then it retrained after 4 days. So it just talked to people for 4 days. And then we come back and retest it and see how much it's better after just talking to people for 4 days versus not. Okay? So for navigation, you're just trying to get the robot to go someplace. And there, that's not a difficult enough task where we didn't really see much improvement from before and after. This is completion rate. In other words, does the person eventually say it did the task correctly? So here, the good system is good enough to start with to get it right 90%. It doesn't really improve. But on delivery, where you have to specify some object and have them deliver that object from one location to another, there's more linguistic complexity there. And so in the beginning, in the first batch, before it's had 4 days of conversation, was it 4 days? it only gets 20% of the tasks done completely. But after the 4 days of conversation, it's much better. It's getting at least 60%. And this is with a real robot talking to real people in the lab. So it sort of shows that this really works in practice as well as just simulation on a mechanical Turk experiment. We also did this survey for the people in the real robot experiment. The robot understood me, a Likert scale, initially not so much, and then after 4 days of talking to people, it's gotten better. Okay, so that's sort of part one. That's a bit of an old talk. That's from IJCAI 16, so it's a bit old, but I think it's sort of interesting to sort of start people on what we're trying to do here. So let's just talk about this paper we had at Coral a couple of years ago. where we had a robot play what we called I Spy. So you put 4 objects here on a table, and you have the person describe one of them here. So this guy describes an empty metallic aluminum container, and the robot has to guess which of these 4 objects the user is talking about, and it gets to pick. And if it gets it wrong, it gets a second guess. And then when it finally gets it right, it says, you got it right. Now it's a learning trial. And then we do it again. And we see over time, by just playing this I Spy game, I don't know how many people grew up playing I Spy. You're in the car, your kids are bored, right? And you say, I spy with my little eye, you know, a person with a black hat and a blue jacket. And then you have to say, it's him. So we're sort of doing this with the, sorry, I didn't mean to pick on. We sort of try to get the robot to play this game with these 4 objects on a table. So they keep making guesses. So here's the robot. It's like, ooh, you didn't get the right. Right. I'll have a better video of this later. OK. So that has to deal with this perceptual grounding. How do we take a natural language expression like, what was it? Aluminum can with whatever it was. How do we get it to map that to the physical properties of that object that the robot can perceive? It's a very complicated problem. So at mapping expressions like empty metallic container, that's called, you know, Steve Harnad wrote this sort of philosophical paper back in 1990. He said, important problem in AI is the symbol grounding problem. How does the computer that's manipulating these abstract symbols, how do they connect those symbols to actual physical objects and actions and events in the world? He thought that was a really critical problem to solve to do AI. And I agree with him, which is why I've been working on it. So there's been a growing body of work connecting language to vision. These are old references. But oh my God, the last few years, this area of language and vision is just, you can talk to William about it. Oh my God, we were just like, I literally get recommended 10 new papers that just got put on archive that day. I'll probably look at my email right now. I'd have 10 more papers recommended me. Just got deposited on archive today on language and vision. It's crazy. Very little work on connecting language to other perceptual modalities beyond vision. Everything's about language and vision. We've tried to push that. Let's go beyond vision. Humans have more perceptual capability than just vision. So we're trying to ground the meaning of words in multimodal robotic sensory data that goes beyond vision. We produce a multimodal feature vector for each object and train classifiers to recognize descriptive words such as empty, metallic, light, all these words. But we're going to use more than just vision. We use vision, of course. We actually use what's called RGBD, right? We use a Kinect sensor that gives us video as well as depth information, right? How far it is to each point on the object. It's called RGBD data. So we use even a little bit more than just vision there. It's vision with depth. Sometimes people call it, 2.5D or whatever. Because you're not going to 3D model the whole thing, but you're getting depth map. We use audio. It's listening all the time as it manipulates objects. And we ask the robot in advance, before it gets to play the game, it has a whole bunch of objects and it plays with them. What it does is it grasps the object, it lifts the object, it lowers the object, it drops the object, and you don't give it anything fragile. It presses on top of the object, it pushes the object, and all the time it's watching, it's listening, it has an audio that's recording the audio, how something sounds when it drops. So you drop something aluminum on the table, it sounds a little bit different than if you drop something plastic. So maybe I can tell whether something's aluminum or plastic by how it sounds when it hits the table. And it has haptic. It has sensors in the robot arms, heavy versus light. Actually, it learns a definition for a full bottle of water because it knows when it lifts up a full bottle of water, the robot arm gets more resistance in the haptic sensors in its arms. And it tries to ground the meanings of words in all the visual data, all the audio data, and all this haptic information. Okay? And then we play this I Spy game with it, where you collect labeled training data. And it's sort of a fun way for the human to interact with the robot and the robot to learn about perceptual words and how they connect not just to visual attributes, but to all this sensory data that the robot can gather about that object. So here's a set of objects we played this game with. 4 folds of 8 objects each. 32 objects in total. It's sort of a variety of sort of various householdy sort of objects. And we encourage people not to refer them by category names, but to describe them in terms of attributes about those objects, and not necessarily just visual attributes. So then we played games with 4 objects at a time. What we wanted to say is, how much does all that extra modality help the system play I Spy better? If it has more sensory data, can it identify objects more quickly than just having vision alone? So the key experiment we ran was only using vision versus using all the modality about all that information about the object when they manipulated it. So each participant played 4 games, 2 with each system. They don't know which system, if they're playing with the vision only or the multimodal, so that's where it's blind, such that the system saw all 8 folds in objects in the fold. And then we measured game performance. Classifiers see novel objects during evaluation. So we leave one of the fold of objects out, and then we test it. It's learned on some set of objects. We don't want to, obviously it's learned about the words used to describe those objects. That's not interesting. We give it a whole new set of objects. How well is it able to play I Spy with new objects? Is it learned enough from all those other objects and the words that people use to describe them to help identify these new objects that it's never seen before? Okay. So here what we saw as it goes on more and more training across the folds of this different amount of training data, the vision-only system, this is the number of guesses it needs to make before it guesses the right object out of the 4 objects in the I Spy game. So obviously we want this to be lower. The vision system gets better, but not very much. The multimodal system gets dramatically better. Of course, what's the obvious question that everybody asks me about this curve? Yeah, what happened in that last fold when it went up? So Jesse looked into this, and if you look at this set of objects ended up being in the test to be the test fold. Does anyone notice what object here looks very different than anything else? That orange ball. So it got that orange ball, and it really screwed up the test in the 4th trial because no one used words about balls or maybe even orange, right? So it's like that object happened to end up in the final test fold, so it really got hit in the performance in that last trial just due to chance, because it happened to get that weird object in the one fold. So I don't think there's too much. Ideally, we would run more trials, but believe me, my students have a lot. They spend a lot of time in the lab working with people, get the robot working. Anyone ever here actually dealt with real robots? Yeah, I mean, it's a pain in the ass, believe me. I don't do it. The students do the hard work, but I watch them struggle. So it's just hard to collect tons and tons of data of this real robot stuff because it's just every experiment is setting all the robot stuff up in the objects and all this. It takes days just to run a small number of trials. Okay. Another thing I've been interested in for a very long time is active learning. I don't know how many people know this term. Most machine learning, you just label a bunch of data and you give it to the system. Active learning says the learner itself gets to select what data gets supervised. It's more actively involved in the learning process. So the idea is we want to incorporate active learning here. We want the robot to be able to ask questions to the human that it thinks would really help it learn. Not just take the data that the human gives it, but ask questions actively to learn better. So there's a whole area called active learning that does this. A very standard approach is what's called uncertainty sampling. You take a bunch of objects in the world, you don't know much about them, and you find out what words you're most uncertain whether or not they apply to that object or not. By most uncertain, it's like, yeah, I don't know. Is this color brown or not? Maybe I think it's 50% chance that someone would call it brown, so maybe that's a good example. I might look at that. I know that's orange, right? I'm very confident. So I wouldn't ask about that, is that orange? But I might ask, is this brown because I'm uncertain? So we had a paper at Coral last year where we incorporated this idea of what we call opportunistic active learning. Most active learning, you have all the data just sitting there. And usually the algorithm can ask about any data in the data point. But a robot is in a particular room at a particular time talking to a particular person. It can't point to just any arbitrary object. It has to deal with the environment that it's in. So we call this opportunistic because it doesn't have all the data available to it. But opportunistically, if it happens to be in a room, I've given an office thing where maybe there's something I don't quite know what word we're referring to. Say I see this object and it's like, I'm in the room and I see this thing and I've never seen a mic before. That'd be a good opportunity to ask somebody, hey, what is that thing? And they say, that's a microphone. It's like, okay, I've learned something. But I've seen chairs before, I've seen cups, I've seen laptops, whatever, but I've never seen a microphone before. So that would be a good opportunity to ask. But I don't have just tons of unlabeled data. It's just I'm wandering around the world, and every once in a while I see something really novel that I don't know how to talk about. And then, that's interesting. I'm going to ask somebody a question about that. That's the idea of what we call opportunistic. So ask locally convenient questions during an interactive task in anticipation of future performance gains. And that question may not be useful for the current task. So I'm sort of sidetracking the human because they want me to, the robot to do something, right? And I'm asking, it's like, what the hell are you asking about the damn microphone for? I want you to get the damn cup of coffee for me, right? But you know, most people are like, hey, that's cool. The robot's asking me questions, you know. So here's how we set up in the lab an experiment to test this idea. So this table down here, the active test set, is the good old-fashioned experiment we had. 4 objects. The robot has to figure out which of these 4 objects the person is talking about. But it has 2 tables on the side with 4 objects. This is what we call the active training set. It can ask questions about these objects. So that it can ask the user, hey, you know, you want me to find the orange ball. And it can point to one of these objects. Is this orange? Is this a ball? Right? Can sort of opportunistically look at the objects around. Can I learn something by asking about one of these objects that just happen to be in my environment? Okay? And the robot can ask questions about objects on the sides to learn object attributes that help it play the game. So here's my first good, robots are great, you have to have good videos. So here's my video of people playing this game. Hopefully the sound works.
Please pick an object that you see between one phrase.
The yellow petal.
Now the audio's cutting out on me.
You said, this is a yellow bottle with filled in it.
Yes. Yes.
We tested the audio and now
Turning
it's cutting.
table 1.
In robot videos, you always see this sped up part because it gets boring to watch the robot in real time, but that's standard robotics video.
Use the word bottle to describe this object.
Yes. Yes.
I see. Can you show me an object that you would describe as yellow?
So it can point to certain objects and say, is this X? It can also say, show me an X, if you can. This thing is just confirming or something. I don't know. There was some agreement.
Can you show me an object that you would describe as bottle?
I told you I was worried about the audio.
Turning the object you had in mind. You said this is a yellow bottle with water filled in.
So we did these 2. One that can only ask about the current task, and then one that can just ask arbitrary questions that it's curious about.
Purple bottle.
Wiggle, use
We call that an off-topic question. If it asks about a word that the human actually didn't use, but they think it might be relevant later.
SE.
Why is the audio messing up? So we call that the inquisitive agent. It just asks sort of random, not random, actively selected questions, but not necessarily about that particular trial.
Bottle with brown pink inside it, red cap.
That's a complicated
Yeah,
description.
object that you would describe.
So it knows red. It's trying to clarify some of these other objects, and you got to speed it up because it gets boring.
Is this the object in mind? And you said a plastic bottle with brown peanuts inside it with the red.
Yeah.
Okay. Hopefully that gives you a little bit of an idea. Again, I'm sorry with the sort of crappy audio. Okay, so that's what gives you an idea of what the robot interaction is like. So we ran this experiment to compare user reactions to a baseline robot and what we call the inquisitive robot. So the inquisitive robot asks more questions, 5 versus 3, and it can ask questions that aren't about the current description. So it can just ask other interesting properties that it wants to learn about objects that don't necessarily relate to what the human just said. And we want to know, how do people feel about answering all these extra questions, and does it really help the system do better? So we ran this experiment with the training over time and how many correct guesses you get in the game. And we found that, hey, this inquisitive robot, actually, not surprisingly, it's asking more questions, but it's asking good questions that really help it learn to do the task better. And overall, it really improves its performance at the task. And then we asked the users, do you think this robot just asked too many damn questions? And, the inquisitive system gets a little higher score on that, but not a lot. People don't seem to mind too much that the robot asks these extra questions. Okay, so that's this idea of opportunistic active learning. We've ran some other experiments that I could talk about to try to show that approach, by asking questions to people, they may or may not be relevant to the current task, but it helps the robot learn, and that over time it helps it get better and better. Okay, so then when Jesse finishes these, I said, you have to put all this stuff together into an actual working robot that solves the whole problem. So we then, at the end of his thesis, he integrated all this stuff together, learned the semantic parsing, learned a complete robotic system from the user interaction while performing the task, and got the whole thing working. And this is the final video that he produced for his thesis a couple of years ago. This audio.
Move knowing from the lounge by the conference room to Bob's office.
Do we want to try to reboot this or something?
Yes.
Let's try to I hate to do this, but maybe if we connect and reconnect, it might get a better connection or something. This is computer scientist, the approach to everything, right? Oh, turn the microphone off when I'm running the video.
Does rattling mean the same thing as empty?
No.
I'm still learning the meanings of some words.
Is that better?
Show me an adjective that use the word rattling when describing or say none of them.
So it's got this command, and it doesn't know a word, so it engages the user in this dialogue to try to figure out what rattling means. And it does active querying to collect training data that will help it understand that command.
This one?
I see. Show me an adjective that not use the word rattling when describing or say all of them.
Watch. This one.
That's Jesse. That's my student that did all this work. Well,
I see. Show me an adjective that use the word rattling when describing or say none of them.
Watch. This one.
I see.
So now it thinks it understands what rattling is.
And now back to business.
this is 8 times sped up because you don't want to watch it in real time. But notice it's navigating all over the building, finding where the hell is that rattling object. Oh, I think it's here. So it's explored these objects before and has the feature vector for them. That's important to know here. So it doesn't have to shake it because it's done that in the past. It's dropped it though. Grasping is a real pain in the ass with robots. Look at this. Look at the way it grasps this. Then looks what it does. It's really stupid. What the hell? I don't work on grasping. Robotics and people need to work on grasping a lot more. Now it says, oh, I got to find that room to deliver it to. And it finds the room to deliver it to. Actually, that's my postdoc Harrell. I don't know why they called him Bob. And it rattles, yes! Okay. So that's like the final demo video. It takes a while to do real robotics research and get everything working. I'm good. Hopefully. Okay. So that gives you a little idea of some of the work we've been doing. Just to relate some more recent work we followed up on this is, it has a fixed policy that it does to figure out when to ask questions, but we've developed some more recent work that actually uses reinforcement learning to figure out what questions it should ask and when it should ask it to maximize eventual goal performance in the long term, which is a standard reinforcement learning problem. So we had a paper at EACL. I'm sorry, that's this. I'm sorry, I'm getting ahead of myself here. That's this paper. I'll go back. So we use reinforcement to learn an opportunistic active learning policy that decides when and what questions to ask in order to maximize long-term reward. This was an EMNLP paper that my student Aishwarya wrote last year. Sorry, I'm doing these in sort of reverse chronological order. Other work we've done in this space is integrate reinforcement learning policy with semantic parsing from Dialog. So there's two problems in natural language. One is learning to interpret an individual sentence. Another one is learning when and what questions to ask and engage in a good dialogue to minimize the number of turns that it takes to eventually figure out what somebody wants and accomplish their goal. There's been a lot of work on each of those individually. No one's tried to put them together before. And it matters because reinforcement learning assumes this task is stationary. In other words, otherwise the system isn't changing. But if you're learning a semantic parsing, then the understanding is changing underneath the dialogue learner, and they get out of sync. So we developed a way to jointly learn both semantic parsing and dialogue learning together. And there's some tricks that you need to get that to work. That was an EACL paper a couple of years ago. Something else that Jesse worked on was, I talked about that concept of light and chair, about words being polysemous. I haven't talked too much about that in this talk. But there's lots of work, of course, in natural language dealing with word sense disambiguation. I see a word like light in a context. Does it mean lightweight or light color? Or I see the word chair in context. Does it mean, a physical chair or the chair of the department? People have done learning of trying to induce what the senses of a word are from text. But we did this work learning the senses of words by looking at not just the text that it is surrounded by, which is typical, but to look at the sensory data surrounding it, what objects those words are used to refer to. And we show that you can learn senses of words much more effectively if you use multimodal data. You use the visual data as well as the textual data to figure out the senses of words. And that's an Ijkai paper from a couple of years ago. The other thing, notice I told you in the beginning, this robot has to explore all the objects in advance and do all these actions on all the objects in order to learn correctly. But ideally, we would only do the actions we need to do to understand this particular word. So Jesse did some work that was in AAAI a couple of years ago. Given a novel word like squishy, use information about similar words to determine what action. So it looks up squishy, and squishy is sort of like in vector space. Here we use standard, vector semantics. It's sort of like, well, it's similar to soft, it's close to hard, because a lot of times in vector space, words and their opposites are actually pretty close in space. This is a classic problem in vector space semantics, is that sometimes antonyms actually appear pretty close in vector space. But it's good enough to know that, hey, squishy, hard, which of those actions that the robot could perform do you think it should do to figure out what that word means? Press, right? So it realized, I I think the action I need to do to figure out whether a word is something is squishy is press it. So then it doesn't have to do all the actions. It just presses objects and says, ooh, I think I found a good discriminator for squishy because when I push on squishy things, they feel different than I push on hard things. So it figures out what actions it needs to do to figure out the meaning of a particular word. Okay, so to wrap up this part, so we're trying to develop robots that learn language from interactive dialogues with users. We've done this work on multimodal language grounding by playing a fun interactive I Spy game that uses more than vision. It uses haptic. It uses audio. It really expands the set of sensory modalities that you can ground the meaning of language in. We're trying to integrate active learning of semantic parsing, dialogue strategy, and language grounding all in a single system that just works by talking to people and helping them solve their problems and answering them, asking them questions, possibly opportunistic haptic questions about things they're not talking about right now, but they think might be useful in the future. And so we think that by incorporating all of this, we can help develop robots that can learn language and know how to perform the tasks we want them to do more effectively. Okay, so I have an extra little addendum that I can add, but maybe why don't we break for a while for questions and we'll see. I have one other project that I can show you another video if we have time, but I don't need to. Yeah.
My question is on the interaction with humans. So anytime a robot engages with a human, it's kind of invasive. It's time consuming. It takes the human's attention. So in the example, one of the video examples, you showed a dialogue where the robot asked to see an example of yellow.
Yeah.
That seems to me like something the robot could just go ask Google. So hey Google, show me yellow.
Sure.
So have you taught or done any work in what could be asked to the web versus a human?
Yeah, well, one thing I should mention is, nobody publishes journal papers anymore, right? But I told Jesse, publish a journal paper on your thesis. That takes a while, right? Literally, finally, his journal paper is about to appear in JAIR. And it's like 80 pages describing everything you want to know about this project. And he does do something like this. So he looks at grounding of words. He can ask for synonyms. So say, what's a synonym of yellow, like marigold or something? I don't know. Say someone uses the word marigold. It can look in vector space and knows to ask. He can also ask these questions like, is marigold is the same as yellow? So it doesn't always try to have to get examples to determine the meaning of a word. It can actually also actively ask questions about whether this word is synonymous to this other word. So I mean, that's not exactly what you were asking about, but yeah. But the point is, this was more of an exercise to push what we could do with just dialogue and not have to rely on a lot of extra resources. But that doesn't mean I'm opposed to exploiting whatever resources you have. It was just this was sort of a way to sort of experiment. Could we actually bootstrap a robot from almost ground zero by just talking to people? Is that the way we'd eventually want to solve this problem? Probably not, but I think it's an interesting experiment to run to see how far we can push this learn from talking to people approach.
Great answer, thanks.
Great talk, thank you. So I have a quick question. So I'm interested in how the agent be able to ask those off-topic questions, and how does it, make sure this is relevant, and how could he inference the result based on the answer he gets?
Yeah, so that's more talked about in this that last paper, the EMNLP 18. Anyway, it has a bunch of features. There's a lot of work in active learning. Active learning looks at lots of things. One is uncertainty bases like margin sampling. So say we have a linear separator as our dividing between two classes. What do you think is more useful? Something that's close to the line or something that's far away? What should I ask about? Something that's close to the line, right? That's uncertainty sample. It puts lots of features about that but you don't want to ask about outlier examples. So the paper describes all these features that we use to maybe determine what a good question is. Then we give all those features to reinforcement learning, and we just have it play these sorts of games, and then it learns a policy for what questions to ask when to maximize long-term reward, which is like the number of tasks I achieve with the minimum number of dialogue turns. So you actually learn the policy. This paper learns the policy for when to ask questions and what questions to ask by just doing a bunch of trials and running reinforcement learning to learn the best policy to figure out when it's worth interrupting a user, that I would learn so much, that I would benefit in the future. in order to maximize my long-term reward. That's a very complicated thing. So we use reinforcement learning to learn that policy for when to ask good questions. Yeah, and if you're interested in that, look at Aishwarya's MNLP paper from last year, or 2 years ago now. I still think it's 2019.
Great talk, and thank you very much. And I'm thinking about there's many topic on vision like that. You can understand in this video, or what does human do in the video. And I think whether the robot can learn from the video that the human can teach them this is yellow, this is red, and the robot can not asking human, but watch video to understanding the world.
Sure, that's sort of like your question. That I'm not against using all other resources to do this. Like I said, this was sort of an experiment to sort of push this dialogue approach as far as we could. But ideally, instead of starting it with 5, but the point is, there's still going to be words you didn't hear. Like I said, that's why I asked about marigold. They say, okay, yellow I can just get from Google, but people use squishy, right? Am I going to have training data for squishy? Probably not, but I can engage in this dialogue. So I think no matter how far we push up the learning curve due to labeled data, there's always going to be this long tail of other weird things that it hadn't seen during training. And this is an approach to deal with that sort of situation. And I'm just showing you experiments where I've pushed it all the way back just for sort of demonstrative purposes. But I'm happy to push it forward, but then I still think these techniques are going to be useful because there's always new things that the robot's going to encounter in day-to-day use that it just wasn't prepared for in the labeled training data. These are the types of mechanisms I think that are going to be helpful in those situations. I don't want to say I want to build a robot to actually start at ground zero, but no matter where we start it, I think this dialogue capability will still be useful to push it further out that Zipfian distribution of all these very unusual things that happen in language.
So 2 questions. For the first project, if you look at the result of one is the delivery, the second is navigation. And it seems that navigation is much easier to learn than delivery. But essentially, you can think of navigation is a subset of the delivery, right? In order to deliver to someone,
you have to navigate somewhere to get the object to deliver,
Yeah, so I was wondering whether you try a variant in the middle, in the sense that, let's say you train a policy that based on the feedback during navigation. And then you start from this updated policy, and then use that policy to guide
the so you're saying do navigation first, and then adapt that policy.
Exactly. It's like a meta-learning approach.
Yeah, that's a fair point. We haven't really looked at that. We're sort of giving it a mix of all these tasks. So there's really no, I mean, there is cross-learning because it's learning meanings of words and other things. It really is a multitask. It's learning both of them together. But it doesn't directly try to use navigation to aid delivery. But it might learn word meanings when it's learning about delivery that help it. I mean, that in navigation that help it in delivery, right?
I see.
Because there's a lot of shared knowledge between these two tasks. So it's doing a little bit of that, but it's not doing it explicitly. But there is a lot of shared knowledge of what the meanings of words are is shared between both.
And then for the active learning project, so I can see that if you want to perform a task that is, say, composable, in the sense that, let's say, if you want to grab a yellow cup, and then if there is some other question that will allow the robot to ask some, not directly the question in the testing set, but ask some subtasks that are relevant to your testing phase. Like you can ask, is that a cup and is that a yellow? Then I can see that it will definitely work.
Sure.
But in the context of like some real noisy problems, in the sense that, so let's say if you are allowed to ask some indirect questions, but that indirect question can contain a lot of noisy, they might degrade your policy during learning. So how do you handle that?
I mean, noisy data is a classic machine learning problem. There are lots of techniques to, regularize and prevent overfitting and all that stuff. I don't know if I have anything extra to add there. Obviously, we try to use the best, learning techniques that handle noise in the training data. Because obviously, all this user interaction, you're going to collect a certain amount of noise. But hopefully, the underlying learning algorithm does enough regularization and overfit prevention using dropout or your favorite overfit prevention technique to hopefully avoid overfitting the noise in the and separate the signal from the noise.
So I'll go ahead with a question. Sorry, go to you. So one thing I'm very curious about is the sample complexity for reinforcement learning, because I think in the past few years, some of our students also look at reinforcement learning for this task. So it turned out that it's very difficult to converge, and it takes a lot of time to
takes
run.
a lot of data.
So I'm curious.
We do all our RL experiments in simulation. We don't do RL on the robot because, you know, there's a lot of work in robotics on sim to real, because you need to learn policies in simulation mostly, and then just fine-tune them on the real robot.
I see.
Because you're never going to collect enough training data. I used to have this joke I gave to reinforcement learning people. I said, how do you know you're a reinforcement learning person? And I said, your x-axis on your learning curves is in scientific notation. You get the joke on this? Yeah. They need so many friggin' trials just to learn the stupidest thing. Like DeepMind runs their damn Atari thing for like days just to learn to play Pong or something, right? You know? So you're never going to get that level of data with real robots. So I think a lot of that has to come from all our things are dialogues in simulation. And then we try to take that policy that was learned in simulation, then port it to the real robot, and then maybe do a few trials there to fine-tune it. But reinforcement learning has very high sample complexity. I think we're only going to be able to do it successfully in simulation, but then you can transfer those simulated the policies learned in simulation, hopefully you can put them on the real robot, and with some fine-tuning with a limited amount of data, you can adapt them. But RL has very bad sample complexity, yes.
What do you think the major research challenges are for your robot to perform as well as a second grader? And then how long do you think it'll take to solve them?
Well, a lot of this is training data, right? So when you do real robots, I think eventually we need a standard platform robot that is widespread across a million homes, and all of them are collecting and pooling their data, you know? And it's just, right now it's hard to run those experiments, but I think eventually when we all have some robot in our home, and it's interacting with all of us on a daily basis, we'll start collecting data at the scale that will allow modern deep learning techniques to really take hold. And so, but it's currently a struggle. That's one thing that I don't like working with robotics, because it doesn't scale well. Just collecting all that haptic data on objects about dropping, and it takes forever just to collect that data. But imagine that we had 1 million robots in 1 million homes doing those experiments on all sorts of objects in everybody's houses, breaking all sorts of stuff. You know, you know, we would collect an immense amount of data that I think we could really learn for. But it's really a little frustrating working in robotics. It's hard to collect data at scale. But I'd like to think when we reach the point that we all do have a robot in our house, then we can really we can make those robots much better, much quicker by just pooling all their collective experience across the robot hive mind, right?
Great. So I think, unfortunately, we're running out of time, but I think Ray's going to still stay here a little while. But just as a token of appreciation, let's thank Dr. Ray Mooney for the wonderful talk today.
Oh, thanks.
And thank you for coming. Thank you for coming.